ça. Steve.
I probably just missed this one, but could you remind me or tell me what is the plan to your Lagrangian style?
Well, if Lagrangian is 0, the only place it could come in would be Lagrangian itself. So in, like, if you use the Klein-Gordon Lagrangian, there's an H bar in the Lagrangian, right? In the coupling constant. So that's the only place it can come in. This kind of worries me that that's not enough. But, and maybe I'll have to relax L equals 0. I've been playing around.
Right, because at one point you mentioned some the tongue energy uncertainty relation, and those are related. Yeah.
Well, I'm using the uncertainty principle to get the result I want. I'm not deriving the uncertainty principle. The uncertainty principle is key for all these retrocausal stories. If you know everything at the beginning, then you're going to signal in the past. The key is that you have hidden variables. They have to be hidden, or else you got retro signal. We're using the uncertainty principle as far as understanding what keeps us from getting at those hidden variables. I don't have a good answer.
Okay, we have quite a queue now. Professor Gissin?
Can we try to apply what I understood from your talk to quantum computation? For instance, this famous show algorithm, which is so efficient, and usually the argument says that the efficiency comes from the enormously large state of the quantum mechanical state. And you tell us this state is so large because the future geometry is open, is not fixed.
As far as we know, yeah.
Yeah, but actually in a quantum computer it is fixed. We know exactly from the beginning which measurement we're going to do. So actually, according to my understanding here, the state is not that large.
That's right.
And so quantum computation should not be that efficient.
Well, that's not the explanation for why you get speed up. I've seen some of the papers arguing that you get speed up from using the future. I guess, I mean, it's not linear, right? If you have a laser cavity and you suddenly have 2 meters, two boundary problem, you can get an enormous enhancement of the field inside, right? So having a 2 boundary problem in time, you can get these resonances that strongly amplify things.
Okay, so you change completely the explanation.
I changed that explanation, yes, yes.
Okay.
Okay, Dustin?
Just a brief question. On one of your first slides, you said that the Lagrangian density itself is a natural local vehicle.
Right.
And the Lagrangian density is not even defined in physical space. Can you explain how it's supposed to be a local vehicle in physical space?
The classical Lagrangian density, say, the Maxwell classical field, can be defined on physical space. Absolutely. Yeah, just think of them as classical fields rather than quantum fields. But you could take the standard model and just interpret every field as a classical field.
Didn't understand that, but then the fields would be the vehicles of the Lagrangian density.
Okay, yes, yeah. The fields, the Lagrangian density and the corresponding fields would all be vehicles. That's correct.
Okay. Ruth?
Yeah, just another clarification on the Lagrangian. Do I understand correctly that's what's supposed to apply to the vehicles?
It's a master constraint. This L equals 0 constraint is a sort of master constraint, getting away from all possible paths to only some possible paths.
I guess I'm missing something because if the Lagrangian is 0 and the action is 0, then, and you want to have some dynamics going on with these vehicles, I'm unclear as to where that dynamics would come from in a Lagrangian 0 action. How do we understand
The best guess, if the argument goes, all you know is L equals 0, that's all you know. Your best guess is your history, which encodes your dynamics, is going to look kind of like your action extremized Euler-Lagrange equation solutions. If that's all you know. Once you know boundary conditions, you know more. You may know, oh, it's not possible that it will fall in one of those. It has to have some anomaly to it in order to get from A to B. So the dynamics are, I mean, it's in history, right? Any history, you can unpack the dynamics. But the dynamics sort of come later. It's like you start with the history, and then you can look at it and say, oh, that kind of looks like these dynamics, or these. But it's not a law-like dynamic. It's not a law-like equation of motion.
Thank you.
Dr. Sorkin?
Yeah, when you mentioned standard model, it reminded me of a question that always comes up in connection with history's approaches, which is what about the fermionic fields? I mean, are you going to set them to their classical value, or I mean, you can't do that with Grassmann fields. So
Yeah.
so what do you have a proposal there?
Yeah, my approach for that, and I'm not very far down this road, is it's, again, far more natural to square the Dirac equation and go to a second order field equation, in which case I think there's hope. But you're right, that if you just have the first order Dirac-Lagrangian, that's not going to work. But that's actually what I'm doing here. I'm taking a first order Schrödinger-Pauli equation. I'm going to second order, introducing more solutions. And the nice thing about that is you get more hidden variables for free along with that.
Would you like to come back on that? Okay. Left 5 minutes?
If I understand you correctly, you heavily rely on the idea of Larry Schulman. And his idea says the following. He doesn't want macroscopic superposition of macroscopic objects.
Mm-hmm.
And he creates a new physics, this new mechanism which will do this. Now, the problem which I see with this line of this problem is that you propose new physics for something which is not well defined. The problem with one Neumann collapse, when macroscopic it collapses, but no one knows what's macroscopic. There is no good definition of what's macroscopic. So the other collapse program tells exactly because of some other criteria what it's had. You cannot take the idea when it's macroscopic, then it will be new physics, because there is no good definition of what macroscopic is.
First of all, Schulman has great respect for the Schrödinger equation and the wave function. And in the multi-particle case, is happy with it being in configuration space. And so we diverge, as soon as we go to 2 particles, our stories are diverging. I'm leaving configuration space aside as an epistemic construct and not thinking about his story for multi-particles. So the where you can compare our stories is for the single particle, for a single spin state. And there, we again diverge in that he wants weird magnetic fields coming in during this rotation. He said there's a rotation, it's got to be caused by something. He has these anomalous magnetic fields flying in to do the job. I don't, I just have non-classical solutions. So we are diverging there a little bit less, but we're not, I had a conversation with him a few months ago, and we're definitely on different planes as to what all this means.
So you don't have this principle that in the end you need a well-defined outcome of the measurement.
Yeah, you absolutely have a for 4 multi-particle states. Well, here let's do an example. Let's do GHZ. So you absolutely have a well-defined outcome. You have explicitly, say in this case, you have the C outcome is in a spin in the plus x direction. The D outcome is a spin in the plus x direction, and the A outcome is a spin in the minus x.
The GHZ, if we define it as big, we understand that in some other cases, things are not so clear if it's macroscopic or not. Or do you have this principle? If you have, then it's not well defined. Or you have some other principle.
I don't need a line between macroscopic and microscopic because at heart all this is classical vehicles. I don't need a line. Even at this level, even it's living in space time. I don't need a line between macroscopic and microscopic. Maybe I do somewhat, but I don't see it.
Okay. Last question, then Brian Roberts.
I was just, as a note on your very last slides, you say, given retrocausality, space-time local vehicles are possible. I was just, I would have commented that space-time local vehicles were on the table since Hogg in the 60s, and there's people that formulated, algebras and observables associated with local space-time regions. And those things do a very good job. I mean, so that mathematized approach doesn't do a great job at producing dynamical models of things like harmonic oscillators. But it does tell you a fair bit about entanglement. And so, at least for the analysis of entanglement, what, can't that also be on the table? I mean, this is, not saying it's an interesting approach, but can't they also be on the table?
I mean, in that story, you still have, it's still all functionals of field histories, right? It's still all a higher level than the field in space-time. It's this field in space-time, and this field in space-time, and this field in space-time. It's not simply this field in space-time. So I don't think it's gone, that is at the level I want it, where at the end of the day, it's like, it's numbers that live on space-time. It still seems to be one level higher. But if I'm wrong, I'd love to hear it. Maybe there's some connection. So.
Okay. Sorry, Professor Salkin. No.
Yes, I'm not sure I understood the Schulman model that you started with. So, is it, it's related to Lev's question, I think, is what's the role of the instruments? So suppose I want to measure Z initially spin and X finally.
Okay.
So I guess the time interval doesn't really matter here, right?
Right, all that matters is the net rotation from Z to X or Z to minus X.
Yeah,
right.
so...
it actually...
Now is the... So, well, yeah.
In my story, it actually showed up, but it showed up as a constant that disappeared.
Okay. So is the role of the instrument to enforce that this beable be either plus Z or minus Z and nothing else at the early time?
Yes, it's
and
a
either
final
plus
boundary
X or minus X and nothing else
right. It's a final boundary condition.
at the final time. But then the instrument is playing an important role.
Oh, yeah.
Because if you don't set those boundary conditions, you won't know anything about the probabilities.
Absolutely.
So I think the question about the distinction between macroscopic, what counts as an instrument, and so on, is a valid.
Okay, so now that gets into the issue, and I'll answer just very briefly, we can talk more online. But remember at the very end I said I had some reasonable arguments of why the external measurements fix the phase. And the reasonable argument is, if you think of that macroscopic system as a system with a bigger rest mass, which it always is, it has a bigger Compton frequency. And so you can look at how much, well, could that frequency shift? And it turns out that no, as long as it's a large mass boundary, you can't shift the frequency, the phase of the measurement device. You're much more likely to shift the phase of the measured, smaller measured system. But we can talk more about that online. There is a macroscopic issue.
There's a second half to the question, which
Yeah, okay, let's, Raphael, go give your second half and then you very briefly.
okay.
Yeah.
So this looks like an initial and a final boundary condition. I don't know if you're thinking of them the beginning of time and the end of time, or not, or can you have three? Because, I mean, when we actually use quantum mechanics, or quite often, you have an update and then you have a subsequent measurement. So suppose you had 3 or 4, and you know.
That works pretty well for this in that the subsequent measurements, a measurement, like a Stern-Gerlach measurement, is going to constrain both the past variables and the future variables.
But suppose it's an incomplete measurement. That's the interesting case.
I'm slowly getting toward those kind of measurements, but I'm not there yet.
Okay, I'm going to stop then, so come back in half an hour. Thank you very much.